Right, good afternoon. Thanks for coming on a short notice. Uh, what we'll do today, we'll try to understand the energy levels, electronic energy levels of naphthalene, and we'll try to see what we can learn about electronic spectra of naphthalene as well. Now, to do this, let us remind ourselves about 2-3 things that we are going to use here. So, first thing that we write, let us say, is Schrodinger equation. I can rewrite this as, say, H minus E operating on psi is equal to 0, right. Now, when I say psi, what I really mean in the discussion of today is molecular orbitals. How do we write molecular orbitals in the level that we are dealing with right now? What is the model that we use for molecular orbitals? What approximation do we use for molecular orbitals? Yeah, louder please. Linear combination of atomic orbitals. So, LCOMO. So, when you use LCOMO, you write it as something like sum over I, say AI phi I. The convention is to write psi with subscript of I and phi with subscript of j, but then I will just write it in terms of one psi for the moment, and then let us see what comes out of it. So, psi here is molecular orbital, the phi's are atomic orbitals. So, you write the molecular orbital as linear sums of atomic orbitals, right. Why do we do this? Because it is not so easy to solve Schrodinger equation. Actually, it is impossible for anything that has too many electrons or is too big or things like that. Okay. Now, the question is, since we cannot really write Schrodinger equation so well, how do I know the energies? How do I know the energies? So, what we try to do is this, we write here say H minus E, maybe I will write like this AI phi I, and maybe I will write A1 phi 1 plus A2 phi 2 plus so on and so forth. Let us say I am using n number of atomic orbitals n phi n, that is equal to 0. Okay. What I will try to do is I will try to arrive at a set of secular equations, so that I can solve this, because of course, there is no way in which I can know all these coefficients from just one equation. So, the common technique that we use in quantum mechanics is left multiply by say phi 1, let us consider all orbitals to be real for now, left multiply by phi 1 and integrate. What do you get in that case? You get something like integral phi 1 H phi 1 minus E integral phi 1 over all space plus, have I missed something here? A1 plus I have A2. What am I doing? I am multiplying the whole thing by phi 1 or phi 1 star and integrating over all space. A2 integral phi 1 H phi 2 minus E integral phi 1 phi 2 and so on and so forth until the nth term A n integral phi 1 H phi n minus E integral phi 1 phi n over all space, that will be equal to 0. Yeah, what was that? Right, this is okay. Now, let us see if we can simplify this a little bit. So, this wherever we have something like say phi I H phi I, we will write that as H I. Wherever we have something like phi I H phi j integrated over all space, we will write Hij. What is this? Integral phi 1 over all space, that is 0, that is 1, right, because we are dealing with an orthonormal set of orbitals, orthonormal set of wave functions, that is 1. But what is this? Integral phi I phi j over all space where I is not equal to j. What is that equal to? That is not 0. Why? Because do not forget the orbitals are on different atoms. We are taking linear combination of atomic orbitals from different atoms. So, my 1s orbital and your 1s orbital, they are not mutually orthogonal. Okay. So, and in fact, we have encountered this when we studied chemical bonding. What do we call this? Integral over phi I phi j over all space where I and j are different atoms actually. Overlap integral, isn't it? So, I can call this Sij. All right. So, in terms of that, we can write this expression. We get A1 multiplied by H11 minus E, then you have plus, okay, I should put a bracket, A2, what will this be? Phi 1 H phi 2, yeah, integral phi 1 H phi 2, this one, what will it be? H12 minus E S12, right, plus so on and so forth. Okay, I have goofed up a little bit, plus An H 1n minus E S 1n, that is equal to 0. S is not a subscript, I am sorry. S1n is equal to 0, right. So, I have got one equation, but then I have n unknowns. How will I find the A's? I need n equations. How do I generate n equations like this? How did I get these equations in the first place? I will have left multiplied by phi 1 and integrated over all space. So, I can do that for phi 2, I can do that for phi 3, phi 4, phi 5, so on and so forth up to phi n. So, when I do that, what do I get? I get a system of equation, and in each one, let me just write the general term here. I will get A1 multiplied by, what will this be? I am left multiplying by, say, the ith coefficient, sorry, ith wave function phi I. Then this will be H I1 minus E plus A2 into H I2 minus E I2, sorry, E S I2 plus so on and so forth, plus An multiplied by H In minus E S In, that is equal to 0. Okay, so, this is a general form of equation where I ranges from 1 to n, all right. And what is common in this family of equations? What are the unknowns? The unknowns are the coefficients, right, A1, A2, A3, etc., etc. So, we have n unknowns and n equation. So, if you have a way of knowing Hii and if you have a way of knowing E, then I should be able to find what these are. Yes. What did I say? S I1, did I write? Oh, I am sorry. No, that was a mistake. It is not equal to 1, you are right. So, this is the peril of copying. I copied from the previous line, there it was S11, that is why I wrote it, that was a mistake, of course it is not. So, Sii is going to be 1, all right. So, I have a system, was that your question as well, Jalada? Okay. So, these are system of equations, and then if you have studied the systems of equation, you know that these are going to have solutions when the secular determinant is equal to 0, right. What is the secular determinant? You do not write this A1, A2, etc., etc. You take this Hi1 minus ESI1, Hi2 minus ESI2, etc., etc., make a determinant out of that, equate to 0, that is the condition. So, that is called the secular determinant. Now, when you do this and if you expand the determinant, you will get an kind of an expression in I, sorry, you will get an expression in E, is not it? Understand what I am saying? You have a determinant like that, expand it, equate to 0, you have an expression in a polynomial of E. What is, which order polynomial is it? N. So, in principle you should be able to solve that and you should be able to find out what it is, alright. Now, of course, we do not want to do that. So, what we are discussing today is, we are talking about naphthalene, and naphthalene is an example of an organic molecule, annular organic molecule, which has a pi electron system. For these, we use another approximation. I think chemistry students know it. What is that approximation that is commonly used for these pi electronic systems? Huckel approximation. Can you tell me what Huckel approximation is? What is Huckel approximation? See, HII is one thing, then you have HIJ, and then you have SIJ. Now, can you tell me what is the value of HII? HII? What do we call HII? What do we call HIJ? Alpha? Which one is alpha? HII is called alpha, and in fact, alpha is said to be 0 in our calculation. What about HIJ? That is called beta. And what about SIJ? SIJ is equal to 0. Is it always 0? Is it always 0? When is it not 0? Let us draw our old friend benzene. Okay. Let me label the carbons 1, 2, 3, 4, 5, 6. So, what we are saying is S24 is equal to 0, but S23 is not equal to 0. So, Sij equal to 0 unless I and J are adjacent to each other. Okay. Does that recall? Does that ring a bell? We recall this now. So, this is the quantum mechanics that we are trying to develop, and we are trying to do it using symmetry. And when we try to use symmetry, again we have to use a kind of an operator. The operator that we are going to use in our discussion of naphthalene is called a projection operator. So, we write it as, say, Pj. So, what does the projection operator do? What does an annihilation operator do? What is the meaning of annihilation? Annihilation. Yeah, it will annihilate, you are right. But how does it annihilate in the language of quantum mechanics? It gives you an eigenvalue of 0, is not it? The function gets multiplied by 0. Similarly, a projection operator, what it does is, if an annihilation operator annihilates, a projection operator would better project. The question is, what does it project? So, what it does is, you take a projection operator and make it operate on some kind of a linear sum. Say, I will write again ai phi I. It is going to give you, it is going to project the wave function that has the symmetry J, right. And what is the projection operator that we have learned? How do we write? What is the form of projection operator? Pj is chi j of r multiplied by r hat, where r hat is a symmetry operation. Chi j of r is the character for that same symmetry operation in the jth irreducible representation. All right. So, that is what we are going to do today, and the system that we are going to study is naphthalene, where your Huckel approximation is going to be applicable. And then if we are going to study naphthalene and we are going to use projection operator, first thing we need to know is what is the symmetry point group of naphthalene. What is the point group of naphthalene? Yeah, D2H, right. So, naphthalene has a planar structure, the C2 axis perpendicular to it we usually call Z, and there are two other axes x and y, they are in the molecular plane. They are also C2 axis, but they are not the principal axis. Which other symmetry operations are there? Sigma h, sigma h is there, anything else? Okay. So, what we will need is we are going to need the D2D character table. Okay. Sorry, D2H character table, I am sorry. So, D2H character table, of course, everybody has a smartphone, please bring up the character table. Since I am a little more old fashioned than you, I will bring out a book. D2H, this is your naphthalene, a D2H molecule. Are we ready? Are we ready with the D2H character table? We are going to need it. What are the symmetry species in D2H? What is the totally symmetric symmetry species? Ag, right, and then you have B1G, B2G, B3G, then you have AU, B1U, B2U, B3U. Okay. Good. So, what is the good thing about D2H? If you look at the character table, there is something nice about it. Yes, all irreducible representations are one dimensional. So, all characters are either +1 or -1. So, if you look at your projection operator, you have to make the symmetry operation operate on the function and then multiply by the character, that becomes very easy. You always multiply by either +1 or -1, does not get easier than that, right. So, let us proceed with naphthalene. So, this is the convention we are going to use. We are going to use z axis perpendicular to the molecular plane, x axis is taken. So, x axis is also called the long axis, because if you look at the molecule, of course, all axes are from +∞ to -∞, but then it is called a long axis because if you look at the molecule has a greater length along x axis and a smaller length along y axis. So, x is called conventionally the long axis and y is called the short axis. Okay. And I think numbering everybody knows. This is the secular determinant for your naphthalene. What is n here? What is the order? 10, right, 10 atoms. You want to solve this determinant, you are going to get an equation in E to the power 10. Of course, it is solvable, you can do it, but what we will see is we do not have to do it. We can use symmetry to break it down into smaller equations. Right. So, here we are, let us begin. While we begin, we will make our problem even easier by recognizing that p orbitals of naphthalene can actually be classified into 3 groups. Okay. But well, even before that, I have spared you some trouble by giving you the answer here. So, ideally when we work out problems like this, what we do is we start with all the 10 p orbitals, make a reducible representation out of it and try and break it down into its components. So, I have done that for you. This is the answer. The answer is this gamma pi is equal to 2AU plus 3B1U plus 2B2G plus 3B3G. So, how many in all? 2 plus 3 5 plus 2 plus 3 10. Total 10 irreducible representations, and that is how it has to be, right, because there are 10 orbitals after all. So, what we will say is, just for the matter of for the sake of convenience, we will say that psi 1 and psi 2 have AU symmetry, psi 3, psi 4, psi 5 have B1U symmetry, psi 6, psi 7 have B2G symmetry, psi 8, psi 9, psi 10 have B3G symmetry, right. And now, let us recognize the 3 groups of p orbitals that we can think of. This is the first group. Will you agree with me if I say that 1, 4, 5 and 8 p orbitals on atoms 1, 4, 5 and 8 form a group. Why? Because no matter what you do to it, C2Z, C2Y, C2X or I, what happens when I apply inversion to atom number 1? Where does it go? Atom number 5. Now, if I work with say pz orbital of atom number 1 and invert it, what do you get? Pz orbital of atom number 1. Yes, it becomes, and I invert it. So, this is the point of inversion. What does it become? Does it become the pz orbital of atom number 5? Pz orbital of atom number 1 after inversion, does it become pz orbital of atom number 5? No, then what does it become? It becomes minus of that. Okay, it is important to realize that we are going to use it, right. So, please remember, when we do an inversion, actually it changes sign as well. It is not just 1 becoming 8, it is P1 becoming minus P8, and similarly P1 becoming minus P5, P8 becoming minus P4 and so on and so forth. All right. But is it possible for any of the operations, sigmas, the planes or the inversion or the C2s, is it possible to take 1 to 6 or 1 to 7? Never. Okay. So, these 4, 1, 4, 5 and 8 form one group. 2, 3, 6 and 7 form another group, and these two groups are very similar to each other, right. Both the groups have 4 p orbitals each. Is that right? Both groups have 4 p orbitals each. So, actually they are going to have very similar symmetries at the end of the game, and we are left with one more pair, 9 and 10. Will you agree with me that 9 and 10 form a group? You perform C2, let us say C2Z, what happens? And let us work with p orbitals. P9 becomes P10, P10 becomes P9. What happens when you apply Px? P9 becomes minus P10, P10 becomes minus P9. Inversion, same thing, P9 and minus P10. Py, what happens when I do Py? When I apply Py, what happens to P9 and P10? Sorry, why I am saying Py, sorry. When I apply C2y, C2 with respect to y, what do I get? What happens to P9 and P10? P9 becomes minus P9, P10 becomes minus P10, alright. So, these 3 form 3 different groups, and also you can, what you could do is you could take phi 1, phi 4, phi 5, phi 8 together, form the reducible representation, break them down, and you will see that they break down into AU plus B1U plus B2G plus B3G. Well, yes and no, they are molecular orbitals, but then when we do a classification like what we are doing now, we are not going to get molecular orbitals, we will get symmetry adapted linear combinations, combinations of which is going to give me molecular orbitals. But you see, when we combine the SALCs, so the question that was asked is this psi 1, psi 2, are these molecular orbitals? What I am saying is they are, but then what we are doing now when we consider these 3 groups separately is that we are not going to get molecular orbitals right away. We are just going to generate SALCs, and then we are going to combine SALCs of same symmetry to generate the molecular orbitals, right. So, coming back to what we were saying, actually there is no need to do this. With a little bit of experience, if you just look at this linear sum, 2AU plus 3B1U plus 2B2G plus 3B3G, right. I can write it as 2 multiplied by AU plus B1U plus B2G plus B3G plus B1U plus B3G. Is that right? So, it actually I can tell right from there that B1U plus B3G is going to be the symmetry of phi 9 and phi 10, and each of these will be AU plus B1U plus B2G plus B3G. Okay. So, this much is done. What is the next step? The next step is to use the appropriate projection operator to generate the symmetry adapted linear combination. That is what we will take up in the next module. So, MOOC है half an hour के इसमें, तो ये पहला वाला मॉड्यूल खत्म हो गया, अभी दूसरा शुरू होगा. Okay, welcome back after a long break. We are discussing the electronic, we are discussing the molecular orbitals, pi molecular orbitals of naphthalene, and what we have got so far is that we have been able to determine the symmetries of the molecular orbitals that we are going to get. We have also been able to break down the constituent p orbitals into 3 different groups, two consisting of 4 p orbitals each, one consisting of 2 p orbitals, all right. And we have also said that the first 2 sets of p orbitals are going to have symmetry AU plus B1U plus B2G plus B3G. The last one will have B1U plus B3G. Now, what we will do is we will use projection operators on these phi 1, phi 4, etc., and generate the linear combinations. But let me stop here and ask you a question. Why is it that, okay, what are SALCs? What are symmetry adapted linear combinations? They are linear combinations of atomic orbitals that give you some particular symmetry. So, now I am saying that I am going to generate those linear combinations by using the projection operator of right symmetry on the one of the constituent p orbitals. How does that happen? Do you understand the question? This is what I am trying to say.